Welcome back to the Hyperbolic Coding Chamber Daily LeetCode. Today is day 50. Wearing the same outfit from yesterday, but trust me, it's washed and it smells very nicely. It smells very nice. But day 50, reflections on yesterday. Yesterday was really funny. And what problems did we do yesterday? I think we did coin change, and the video was called Coin Change Beatdown. It was a beatdown. We did very good on that problem, but we didn't do very good. We solved the problem, but it was very suboptimal time complexity. I'm gonna challenge myself next time I run into that problem to give it a beatdown, to give it the best that I have, or maybe we'll aim for the highest time complexity. Or not the highest. We'll aim for the best time complexity, which is the lowest, and we'll aim for pretty much to do better. Any time complexity that would be better than the current time complexity, which we're also still having trouble calculating. So if anyone knows the time complexity of the coin change algorithm that we wrote yesterday, that would be nice. I'm having some trouble figuring it out. That being the case, other reflections. We did coin change. We also did clone graph, which is a good problem. It's a really good problem, but I want to find a way to do better on that problem. Explaining it, pretending like I'm explaining it to someone else helps a lot, so that's pretty good. But I think there's a better way to go about this. But I think some of the problems we've kind of stagnated on because we figured out a solution and we just keep explaining the same solution, which helps us get better at figuring out other solutions. But I want to also try and challenge myself to be able to take the problems to the highest level, I guess. Maybe we'll be able to get a little bit more, work that creativity muscle to get better. That being said, previous comments, on the last video, this comment is hilarious to me. Okay, breaking news. Also, this comment is actually true. The HCC, which is the Hyperbolic Coding Chamber, is currently in the talks with Elon Musk to acquire SpaceX and Tesla. This man put and his 3 ex-wives. This is actually true. We are in talks with Elon to acquire SpaceX and Tesla. Negotiations, it's been me, Copy Ninja, and I'm just that guy in the room. With Elon, the talks have been going crazy. It's a battle, right? We're in the conference room 7 hours, right? And it's just getting crazy. It's just getting crazy. So we need to figure out. And additionally, in other news, the HCC is currently receiving shutdown threats from the U.S. governments. It's just true, a true statement, right? As the sheer number of members poses a risk to the nationwide network infrastructure. This is actually true, okay? That's why I can't leak my location, because Comcast or Comcast, AT&T, Bell Labs, they are after our location because they want to shut down the root cause of the HCC. This channel, when I record these problems, it's actually through a VPN. That's through another VPN, right? Streaming through another VPN, right? So you're actually screen sharing my screen, but this is actually a screen share of a screen share. This is how much we're wrapping down the situation. The HCC, it's growing too quickly. I think we have almost a third of the US population within it. Messages are constantly exchanging. At this point, we're a pretty large source of Discord's revenue. So yeah, it's a big problem. A good problem to have though. So what can we say? The HCC is a problem. The Hyperbolic Coding Chamber is a problem. But this comment is this is actually true. This is not subterfuge. This is actually true. So that's why I never show the HCC on the Hyperbolic Coding Chamber Discord on recording, because when I actually open it up, I actually have to close all applications on my computer, right? As it's loading the sheer number of members inside the Discord. Actually true. So yeah, it's important. Make sure to join. There's a lot of secret cheat codes. We just dropped. Someone just gave us another cheat code the other day. If you type this into your IDE, right? If you type this into your IDE, right, during an interview, during a LeetCode problem, right? Even at work, I mean, it automatically spawns a GPT-4 instance, not 3, 4. This is unreleased GPT-4 instance and solves the problem. You're gonna need that, especially as these coding problems become more and more difficult. So honestly, yeah, if you're not in Discord, you're missing out on the codes. You're missing out on a lot of secret information. But yeah, you might want to get in soon because yeah, the US. I mean, we're in trouble. So we'll keep me and the council, me the copy ninja, and just that guy. We're gonna keep you guys in the loop, and hopefully we'll be able to get some more spots from Discord. But yeah, W comment. In terms of problems for today, we have number of 1 bits. This is a good problem. I can already feel the solution. I don't think we can do any better here. I do not think we can do any better here, especially since we were able to kind of I don't know if this is what they call upsolving, but we kind of been able to solve it, read the solution, fail to solve it, read the solution, solve it. We're not really getting to work our creativity muscle, which is a really, really important part of the solving paradigm. But that being said, this is a relatively simple problem, and it remains to be seen, right? If I had blocked myself with this problem and tried my hardest to create to try to figure out the best time we could use it for, the best time we can do for this problem, would it be the best use of our time? I think the question is no. It's not a very difficult problem, and I think linear time is close enough to a good enough solution. So challenging ourselves for better than that, I don't know, that might be diminishing gains. Ow, my sides hurt. But that being said, we have some random problems lined up afterwards, and it remains to be seen what our goal or base time complexity on those problems are. So it could be a lot of gains to be had. We still have these 10 tabs here, right, that we need to get through. Most of these are solved, but we still have a backlog of review problems to get through, and to get those to optimal time through sheer brute force of work is a necessary evil. So that is what we will aim for. And yeah, I mean, make sure to join the Hyperbolic Coding Chamber Discord. It is very hype, very, very dope. And yeah, it's also dubbed HCC. We also have a very, very cool Discord profile that you might as well click the invite to see because it's pretty cool. And then, yeah, I mean, we're just going to jump into it. I'm doing a slightly shorter session today because I plan to do maybe some more later. That probably will not be recorded. But yeah, I gotta mix up the other preparations. I'd like to learn more about other things too, just other stuff like deployment and designing scalable systems. There's a lot of stuff I don't know about, so that's what I'm trying to. I guess you can gain the most by polishing your weakest areas, and I'm really weak on that just in general. So that could be something I would get better at, hopefully. And then I'd like to do some front end stuff, and then some back end stuff, hopefully. But first, we have to complete our conquest of LeetCode. Right? There haven't been many conquests in totality of LeetCode, but it must be done. And yeah, we're gonna jump into it. Day 50 daily LeetCode. Let's do it. Starting the timer. So we have number of 1 bits. So write a function that takes an unsigned integer and returns the number of 1 bits it has, also known as the Hamming weight. So let's map our problem to our example. Note that in some languages such as Java, there is no unsigned integer type. In this case, the input will be given as a signed integer type. It should not affect your implementation as the integer's internal binary representation is the same, whether it is signed or unsigned. In Java, the compiler represents the signed integers using 2's complement notation. Therefore, in example 3, the input represents the signed integer -3. I think I see what they're saying, because in 2's complement, you flip all the bits. So all these ones would become zeros, and this one would become a 1, right? But this part of the 0 is actually the 2, right? A 2-bit. So we'd flip that, we'd have a total of 2, but in 2's complement, you flip the bits and add the 1, so you end up with 3. But I'm not, oh yeah, and I guess it would be, maybe it's automatically negative as well in 2's complement. I'm not exactly certain, but to map our problem to our statement, right, we're given an unsigned integer. What are our constraints? The input must be a binary string of length 32. This function is called many times. How would you optimize it? Okay, so the function takes an unsigned integer and returns a number of 1 bits. So we have n here, which represents the number 1, 2, 3, 4, 8. Looks like this represents the number 10. No, 11. Yeah, it represents the number 11, right? And we want to count the number of 1 bits, which would be 3. Right, in the second example, we want to count the number of 1 bits, which is actually going to be equal to 1. The number of 1 bits here is actually going to be equal to 31, right? So can we guarantee that our input is going to be 32 bits? It looks like we can. If that's the case, then to generate some ideas, I think we could do this in linear time by visiting every number in the, every bit in the binary representation of the number. And if that's the case, we'd want to keep track of this variable ham, which would be the Hamming weight. We'll return ham, but the way we'll visit every one is by bit shifting. So we know that we're going to be given a binary string of length 32. So if that's the case, we'll do I is equal to 32. I is equal to 0. We're going to want to do 32 operations. I is less than 32. I plus plus. And then what we'll do is we'll say ham plus equal, right? And we're going to want to take the bitwise AND of the current number and 1, right? So then we do n and 1, right? And by masking it, we're going to check if the last bit, right, in n, right, ANDed with the bit 1, right, the last bit, which is just 1. 1 and 1 would give us 1, so we do plus equal 1. So we can do plus equal n and 1, right? But we also want to take that value, right, this n value, right, and bit shift it down 1 so that on the next iteration, right, it turns into this, then afterwards this, then this, and then eventually we'd find the other 1. To do that, we can do n is equal to the n, but bit shifted to the right once. And I think that this makes sense to start. And I think our time complexity here would be linear time. So that makes sense. I think if we do the follow-up, if this function is called many times, how would you optimize it? Now I think you could optimize it with some bitwise magic. So if we have a number, let's just say 1011, this would actually represent the number 11, I believe, in binary. Right, but if we actually wanted to flip the last bit in 1, we could do it by, I think the trick is to take the number, right, which would be 11, right, subtract 1, and it actually becomes 0B1010, right? And then we can actually AND 0B1011, which is 11, right? And 0B1010, right? And if we AND these together, what we actually get is 1, 0, 1, and 0. So we actually can flip that last bit by subtracting 1 from it and ANDing it, right? So what the time will end up taking will actually be, so here we always take 32 operations, but in this new version, our time complexity is going to be linked directly to how many 1s exist in the number, which is a better time complexity, which is technically this is still constant time, since we're going to do 32 operations every time. But to do a minor improvement, we could do, even if there's 6 ones, we'll only do 6 operations instead of 32. Right, and I think we can follow this through and continue it. So we'll have 10 here, right? Right, and if we subtract, right, if we do 10 minus 1, right, we'll actually get 9. And to represent 9, right, we'd subtract 1, right? So 10 minus 1 as this value would actually be, oh, we want to keep that 1 back. We'll change this to 0, change this to a 1, this to 0, and change this to a 1. So actually have 9, right? Oh, no, this is not represented. This is 1, 2, 4. Our original representation should be like this, right? 9 would just be changing this to this one at the end. Now, if we do 10, which is 0b, right, 1 0 1 0, right, and we do a bitwise AND of 0b 1001, we get is 1 0 0 and 0, right? And then, right, if we keep going, we'll flip this, we'll subtract 1, right, we'll get 1, we'll subtract 1 from 9. So this will be our ANDed result, right, with our original value. Right, then we're going to want to subtract 1 again. So this value represents 8. Oh no, this value represents 1, 2, 4. Yeah, right, it represents 8. We're going to want to represent 7 now. So it would change like this, 1, 1, right? And if we AND that with our original value from before, right, and 0, 1, 1, 1, we actually end up with is 0. Oh no, our original value was so we get 0, 1, 1. This represents 1, 2. This represents 7. Let's see, we want to AND 7 and 8. If we AND 7 and 8, right, this should give us 0, 0, 0, 0, right? We did this operation 3 times, right? So it does allow us to count the number of 1 bits. So to change that, we would have a while loop instead. We're going to want to do this while n does not equal 0, because this number is actually going to change it. When n equals 0, you want to stop. Otherwise, we'll do ham plus equal 1, right? And then we're going to modify n and say n, right, is going to be equal to the n minus 1. And this should eventually get us to 0. So it's marginally faster, but in terms of time complexity, this would take the number of 1 bits. So we could make a new variable called b. It would take O of b time, where b is the number of 1s in the bit, which would be significantly less time. Maybe, right? Maybe not for a 32-bit integer. We're just saving, right? It really depends on how many 1 bits there are. But worst case, right, if there's 32 ones in the original length of the number, this approach and the previous approach this approach and the previous approach actually aren't much faster. key idea here is to realize that for any number n, doing a bitwise AND of n and n minus 1 flips the least significant 1 bit in n to 0. Right, I'm realizing now in our original explanation, we were actually doing it in the wrong order. We were ANDing it and then subtracting. We want to subtract first and then AND. So that looks good. So ON matrix, talk through this brute force approach, ponder on the BFS approach for a little. So I think our best approach so far is M by N. Because for every particular indice, right, we're going to do M by N. We're going to do that twice. So it's M by N to the M by N, or M by N squared. Could we come up with an M by N solution or anything better than that? I think this is probably what we'll end up spending most of our time on. I don't know if we can do better than that. I mean, we know that there's it's possible to do better than that in the solution. So we've read the solution before, but I don't know if it's possible for us to figure it out. But we can try our best, right? So I think we're going to skip the, maybe we'll do the brute force approach to start. We'll do the brute force approach to start and then see if we can do better. So given an M by N binary matrix, mat, return the distance of the nearest 0 for each cell. The distance between two adjacent cells is 1. So let's map this statement to our example. So we're given an M by N matrix mat. We want to return the distance of the nearest 0 for each cell. We start with 0, 0, 0, 1, 0, 0, 0. So our input mat is this input right here. 3 zeros, 1 0, 3 zeros. And then we return the same thing. I guess for each cell, the distance to the nearest 0, I guess, is itself, so it's 0. But for this cell, distance to the nearest 0 is 1 block away. And so the distance between two adjacent cells is 1. So that's interesting. For this second example, our input is 0, 0, 0, 0, 1, 0, 1, 1, 1. The output is 1, right? Because the nearest 0 for the center one is going to be 1 away. But for this one, the nearest 0 is actually going to be 2 cubes away. I think it can either be this one, or this one. Our constraints are that m is equal to mat.length, n is equal to mat sub I.length, but they're saying that it's basically a matrix that is guaranteed to have the same number of columns for every row, which is important. So we know that m comma n, right, we know that we'll at least get 1 row and 1 column, and that m by n is, m multiplied by n is at least 1. And mat sub I sub j is either 0 or 1. There's at least 1 0 in mat. Interesting. So I would say one way that we could solve this, right, is we could just do what the problem says. So we're given an m by n matrix. We want to return the distance of the nearest 0 for each cell. So what we could do is iterate through the matrix, right? And it says for each cell, but if a cell is already a 0, then we can presume that its distance to itself is also 0. So we're going to want to say if cell, right, equals 1, right, then we're going to want to say find nearest 0. So if we want to find that nearest 0, what we could do is iterate through the matrix again and just take the minimum distance we've ever seen. So for example, if we go through, iterate through the matrix, right, we'll find this first cell, which equals 1. Then we're going to iterate through the whole matrix and find the nearest 0. Now I think that would actually be the absolute value of x1 and y1 minus x2 and y2, right? And let's try that for this cell right here. If we take the cell in the center and the cell above it, right, the set cell, like 1, is equal to the value or the coordinate in the matrix 1, 1, because it's in the 1th index in the 1th row, and then the 0 above it is actually in the 0th row in the 1th column, or the 2nd column, which is the 1st index, or the 1 index in a 0 indexed array. Now if that's the case, how could we derive a distance of 0 using these values? I think we can see here, right, if we take our starting cell, right, we take our starting cell and then we do x1, which is 1, minus, so if we do x1 minus x2, 1 minus 0, right, we actually get 1. And if we do 1 minus 1, y1 minus y2, we actually get 0, and the distance is actually 1. Well, I think we're going to want to do the absolute value here. And add them together. So we could have another function which calculates distance for two cells, right? Distance function, right? x1, x2, y1, y2. Now it would calculate the distance, right? And then what we'll do, the find nearest function will just iterate through the matrix for a starting cell. So we'll say nearest 0, right? It'll take the matrix, the starting row, the starting column, right? And it's going to iterate through it, right? And return a number, right? Using this math.min, and we'll iterate through matrix and we'll keep a running minimum. We'll keep a running minimum. So I think this solution makes sense to start, so we could try and implement it. The time complexity here would be m by n squared, since for every cell in M, right, potentially that could be up to every element in the array equaling a cell of 1. We're going to have to do m by n operations, which is visiting the entire array. So replace this with iterating over the entire matrix, like row equals 0, row is less than mat.length, row plus plus. And we'll duplicate this again to do column, right? Col is less than mat sub row.length. We know that they all have the same column length, but we'll do it this way anyway. We're going to need 2 square brackets, right? And like we said earlier, right, if mat sub row sub column equals 1, and we don't have to validate that mat sub row sub column exists, because we're going to be iterating within the bounds of the array, within the bounds of the matrix. We said if cell equals 1, right, then we want to find nearest 0, so we said mat sub row sub col equal to find, maybe we'll just call this function nearest 0, and like we said, we'd pass in the matrix, our current row, and our current column. Right, and so now we want to kind of implement this nearest 0 function, right? And we can duplicate the type information for our matrix, which would be an array of numbers. We're going to take R, which is going to be a number signifying the column, signifying the row, and number, which will, C, which will be a number signifying the column. Right, and we're going to return a number which presumably would be the nearest 0. So let's iterate through the matrix again, and we can copy this loop here. And then what we'll do is we'll say if the row subcolumn is a 0, right, then we want to calculate its distance with our running minimum. So we're going to need a running minimum. Since we're going to be taking the minimum, we're going to want to start it at infinity. And it's just because if we do the math.min, we'll know that any value we run into will be less than infinity, whereas if we started at 0, we'll always end up with 0 as our min. So we don't want to set this like we're doing down there. And what we're going to want to do is say min is going to be equal to the math.min of min, right? And this is where we're missing an implementation for our distance function, right? And so let's try and implement that function now. Say distance, right? x1, which is going to be a number, y1, which is going to be a number, x2, which is going to be a number, and y2, which is going to be a number, and it's going to return a number. And it's going to return math.absolute value of, like we said, x1, which is going to be the starting cell, and y1, which is going to be, x1 and x2 of the current cell, right, that we're iterating through the matrix with, right, plus the math.absolute value of y1 minus y2. And so now we can use this distance function here, and our starting cell is always going to be R and C. Maybe better variable names would be SR and SC for starting row and starting column. So we'll pass in SR and SC, and then we're going to want to pass in row and column, which will be our secondary X2 and Y2. And we'll take the minimum of that, and that seems to make sense for now. And then they want us to return that matrix. So let's try this. For let call row on line 20 calls us in mat_row.length. Oh, and we're also doing row plus plus here. We're going to want to do call plus plus, and we actually copied this line, so it's probably the same. And it's saying that mat_row.length is actually doesn't exist. Oh, now, okay, right. Probably because we were adding and we were going out of bounds, which makes sense. So this does work. The time complexity of m by n, and since we're modifying the matrix in m by n squared, since we're modifying the input matrix in place, I guess it would be constant space, but I guess it depends on how we process that. Now, I think the question is, can we do better? Can we do this in one pass? Can we optimize this at all? So we have this matrix, right? And could we reuse our values? Right? Let's say we started with the zeros. Right? Because right now we have to revisit, for each cell, you have to revisit, right, the closest zero. And find the nearest zero. Is there any way that we could, is there any way that we could cache this somehow? Because I'm thinking maybe if we iterate through the array, right? If we iterate through the matrix and we find a 1, maybe we use a map, right? And maybe somehow we can tell for a particular cell, right? We can use some sort of new distance function and pick the nearest zero. That would require a one pass. Maybe we're onto something here. That would require a one pass hashed start for the location of all the zeros. We want the space to be able to fill, though. What I'm thinking is, what if we do a first pass through and we create a map of all the indices to zeros? Maybe we could do something like this. 0, 0, right, is 0. 0, 1 is 0. 0, 2 is 0. Then we'll have 1, 0 is equal to 0. Right, and then we'll have 1, 2 is equal to 0. Right, now when we're iterating through this array, through this matrix, or I guess this particular array in here, if we're at cell 1, 1, we should know where our nearest 0 is, I think. Right, so we need to do two things, right? It's possible that our nearest 0 is past us, which we haven't visited before, but since we visited the entire matrix once, we could know if it's potentially after us, right? And because of the nearest 0 function, we can assume that this is sequential. For example, if there's, the positions of the zeros never change. They can't change. Right, so we know that we could find if we do a one pass through it, we'll know that we can check after us, right? So that's what that map allows us to do. Maybe we can check in place. So we can check after us, right? Well, we could do 1, right, a particular index, right, 1, 1. And what if this was sorted? Maybe kind of like we would do kind of like a map, but we also have an underlying linked list interpretation that allows us to pretty much instantly jump into a particular location into the linked list and check forwards and backwards. But maybe what we want to do is find the closest. We want to find the closest indice. We want to find the closest indice. So you'd have our cell, which is 1, 1, right? And what we want is to 1, 0 and 1, 2, right? And now that I'm realizing we actually don't even need a map, what we're really only interested in is in the cells, because if they exist in the cell, we know they point to a 0. So we know that all of these exist. What we want to do is be able to instantly pretty much find our closest cell. So if we know that our current cell is 1, which it is, right, then the closest 0. So what I'm thinking is if we do it like this, and the closest 0, right, if we start in this set, right, for this particular row, go to this row, right, if there's any numbers in this row, right, we could, right, so even if we go to this row, it might not be the closest one. It can't be the closest 0. We could do a slight optimization where instead of, we could do a slight optimization. Instead of visiting, we'll hold on to this map idea. Instead of visiting every single value in the array, what if in the matrix, what if we just visit all the zeros, right? What if we just visit all the zeros? So this should be a little bit faster, right? Because even up here, even though when we visit through nearest 0, we're only interested in it equaling 0, but we still have to visit the entire matrix. So maybe there's a way to trade time for space, space for time here. Maybe there's a way to trade space for time there if we only visit the zeros. Even if we're doing a no-op in terms of like mat row call equals 0, if we don't have to visit all of them, that could really be helpful. So maybe what we could do, yeah, let's run with that. Let's see if we only visit zeros, is it an improvement? To do that, we'll have to do a one pass. I have to do a one pass through. Right, so we'd have to do a one pass to keep track of all the cells that are zeros. So we could have zeros, right, is equal to an empty array, but it's going to be an array of numbers. And if it equals a 0, right, but now we're trading, well, yeah, it could still be less calls, right, because we did basically we're actually doing 2 m by n, right, here, and then another m by n squared, right, nearest 0, but presumably maybe we're saving iterations by not visiting every one. So right, this would be short because we wouldn't have to visit every single one. We don't have to visit all the zeros. What we could do is do zeros dot push, and we'll push a tuple of row and call onto it, right? And then you could also have non-zeros, right? Then we wouldn't have to iterate through and find all the ones. So what if we did the same, but for the opposite, we could do non-zeros. We'll do else, right? We'll just duplicate this line. We'll do non-zeros dot push, row and column. And now when we're calculating nearest 0, we can just do for const x1, right, y1 of non-zeros, and then say mat x1 sub y1 would actually get the value of nearest 0, right, which is actually going to be, we're going to change it, right, instead of mat, we're going to pass in the array of zeros and our current x, y, and y1. And then we're going to just turn these into a comment for a moment. And then this is still going to be an array of numbers. We're just going to call it zeros. Let's say for const x2, y2 of zeros. We'll delete this line, paste this line here, delete all these extra brackets, and we'll take the math.min of the distance of SR and SC of row and column. And I think that this should be faster. Line 15, cannot find row and column. It's my bad because this is technically x2 and y2. So it's 500 milliseconds faster, which makes sense because it's really is a minor optimization. It's approximately the same time, and it's really hard to know how much of a difference in speed because LeetCode's algorithm running tends to be quite sporadic. So we'll run it twice. Maybe we'll take the average. Right, so now it's even slower this time, and that just goes to show the variability in the speed. Either way, I think what we're getting at is this is really a minor optimization. It's not really going to change. So maybe searching for algorithmic optimizations is not the wave. We want to search for optimizations that have a potential to make it a significant difference in terms of time complexity. So by saving the ones and the zeros, I mean, then it just becomes, I think it just becomes number of ones times number of zeros, because for every one, right, we're going to visit all the zeros. So it's going to be number of ones, right, times should be number of ones times number of zeros, but this ultimately I think is maybe still the same, or it's not too different, or it's hard to know, right? What's the worst case? The worst case is that the array is filled with ones, right? If it's filled with ones, we end up doing m by n, right, against a singular zero. Maybe our worst case in this case that it's half and half, which means we end up doing m by n over 2 times m by n over 2 calculations, which in the end is still m by n squared. So I think that's why the time complexity is relative. It's minor optimization. Well, how about, I mean, if we change the nearest, if we have the zeros, right, and we say that a zero, what if we use the zeros to carry distance, right? So we know that for this one, it's one distance away from a zero, right? So this is 0, right? And we know that this one is a 0. What if we use the ones themselves to carry distance? That way, if we run into a 1, right, we can actually add it to our zeros, right, as a way to speed it up. So basically, if we calculate, for example, this one right here, actually doesn't change because we end up our current algorithm end up iterating over all the zeros anyway. I think we were on to something with the linked list and the map, right? If we set up our map like we did earlier, right, 0, 0, 0, 1, 0, 2, 1, 0, 1, 2, right? And let's say we want to find the nearest 0 for this one here, which would be at cell 1, and it'll be at cell 2, 1, right? Well, the greatest cell value that we have is 1. So if we want to find the nearest 0, right, and it's greater, so maybe there's a couple cases, right? Current cell is greater than max cell, right? If current cell is greater than maximum cell, then the distance is just the closest cell. Maybe it's not that simple. right? The closest max 0 cell, or max 0 cells actually be 1, 2, right? In this array, it's the same distance. What if we had a rectangular array? Maximum cell would actually be this one. Current cell is the max cell. So that is actually not that simple. We'd have 1, 2. Can we do better than that? We have a current cell, right, which is 2, 1. We have a current cell which is 2, 1. How can we access, right? We can, if we have our current cell which is greater than our maximum cell which is 1, 2, right? We can't just choose the biggest one. So that is too simple of a instruction set. Want something a little bit more complex. I think the problem is also representing it as representing a pretty much a column, a matrix, right, in a linear data structure, which kind of removes part of a dimension of the problem away, which can be good, can be bad. But I think the problem being that when we get into this cell and we start searching backwards, it actually doesn't help us, since it's possible that a cell above us or below us, which is not possible since we only have 1, 2, above us is actually closer, but we won't know that until we get there, which actually doesn't help us. Okay, I think we found a solution. This could work. What if we did, instead of doing m by n every single time, or even, so we're doing m by n squared, what if for a particular cell, right, we actually do n iterations? So now it would be m by n to the n, right? Now this would be actually be much better. This would be this would be significant optimization, because we'd be pretty much subtracting a dimension, right? Depending on how large it is. What we could do is, what if we, from this particular cell, right, we could start 3 depth first searches. The first one would check, it always checks the length of the row, right? And if we check the length of the row, right, and if we find any 0, then we know that our answer, if for this particular, so we know that we can check up, down, and our current row, right? We check above us, we can check left and right, which we can just do. It's going to be linear time, right, where n is the number of columns. Linear time here, n is the number of columns. Linear time here, n is the number of columns. So for every cell, we can do 3n, right, in the best case. But in the worst case, we actually end up visiting the entire, right? We want to optimize for the worst case. In our worst case, so I think that, okay, so we can actually do this. In the worst case, I think we can still guarantee m by n to the n time. So we'd have 3 cases. These 3 cases would be, we'd start in the center, right? The first case, right, is that our current cell is actually less than our max cell, and our smallest, so it's actually in between, right? Our current cell is greater than our smallest cell, but less than our max cell, right? So an example of that would actually be if we change our input to 1, 1. An example of that would be this node here in the center, right? It's greater than our smallest cell, which is 1, and less than our maximum, or we'll say less than or equal. That's part of it. And it's less than or equal to our max cell. This is perfect because that means we can do what we said earlier, right? We'll search above us, right? We search above row, current row, and below row. We search above row, current row, and below row, right? We should, the current row will just be a linear time check, right? It's not going to be cascading, but above and below, we're going to want to keep going until we find those values, right? We're going to keep going pretty much upwards until we find those values, until we find a 0, right? And the first, can we assume that the first 0 we find is the best we can do? Yes, no. So if we visit through all the zeros in a row, right, we know that if we found a 0, the shortest path 0 exists somewhere here. And actually, let's check that. I wish we had a bigger matrix or something we could draw on. If we check that, we'll have 0, 0, right, and 0. If we imagine we had 2 more cells here, 0, 0, and 0, 0. Right, and it's actually, so as long as we find a 0 in the cell, right, the problem is there could also be a, for example, if we're on this cell right above us, right, and let's say this is all 1s, and there's a 0 here, and there's a 0 here, the distance here is still, what would the distance here? We have 1, 1, and 0, 0. Right, so distance here is still 2, distance here is still 2. So it actually still works. Distance here would be 3. So that would be one case. The other case is when current cell is neither of those, but it's less or it's greater than max cell. So if it's greater than max cell, right, so our current cell, let's say our input, right, for this would be input would be 2, 1. It's greater than our maximum cell, which is 1, right? Row wise, it's greater than our maximum cell. So what that means is the closest 0 must be the 0, right, that all the zeros in the last array. I mean, all the zeros in the last row, right? And it's true, the closest 0 is either this one here, or this one here. This one's not even worth checking because it's either this one or this one. So if it's less, then we just want to search last available row, right? And then we can duplicate this. Oh my God, I think we're having a brain blast. If current cell is less than the maximum cell, right, then we want to search first available row, right? And since we're iterating through this sequentially, right, we're still going to need that to be the case. So I think this could actually work. What would the time complexity be? I think it would be, we'd have to visit all the 1s in the array, all the 1s in the matrix, which in the worst case would be n by n time complexity, but we want to also visit, every number in the matrix, and for every number in the matrix, we'll do at worst case, in the worst case, we have 3 cases, right? In the worst case, we're in the center of our matrix. We have a 1, and we have to keep searching. We can actually right, we have to keep searching. In the worst case, I think we have m time, because we're searching up and down, which is going to bound us by the columns in the array, right? So we would have n time, I think, which is the column. It's n by m, or m by n, m actually. So we have m time to search upwards, right, and downwards, which is really m over 2. So we have m over 2 time to search up and downwards, and we visit a particular row. We know that this row will have zeros in it because we're optimizing that into it. And I think we can still optimize it without keeping track of the zeros. I think another version of this where we use a depth first search, we actually start a depth first search in 4 directions, which ends up being pretty crazy. Ends up being pretty crazy to time complexity wise. We end up searching the entire matrix. In this version, for a particular cell, we visit our entire row, the row above us, and we keep going until we find a value. We keep going below us until we find a value. Keep going below us until we find a value, and I think that would be m time. What we have to do for every m, for every row we visit, would be m by n time. So maybe it's still worst case m by n time. Where in the previous one, it was going to be n time. So I think we still need, we need this linked list to map a row to an array of cells, and we'll just have to work with these that we had before. And in the worst case, since we only have cells that have zeros, right, in the worst case, right, even if our zero is at the top, we don't have to travel through ones to get there, we'll just start there. So I honestly think the worst case is m by n to the 3n, which would be m by n to the n. So we'll say for this approach, it'll be m by n to the n, which should be much better than our previous one. So we'll need a few things to make this happen. We're going to need access to a map, right? This map, like we set up here, but we're going to want to have, for every cell, for every row, we're going to want a map, an entry in the map, right? So for example, we have 0, 0, right? For row 0, we know the numbers that have zeros are 1, 2, 0, 1, and 2, right? And then for 1, right, we have 0 and 2. And so I think this ends up being pretty good. I think our minimum column will not always be 0. So we'll have to keep track of that. So to create this map to start, so we'll have this map, right? And then when we find something that equals 1, we're actually going to crack this, or crack open this nearest 0 algorithm, and I think we should get m by n to the n time. So we'll have non-zeros, which we will be interested in. And we're going to want to set up this 0 map. It's going to be a new map of number to an array of numbers. right? And if it equals 0, then what we're going to want to do is say const r is going to be equal to if the map already has an array for this row, right? Then we're going to get that array. Otherwise, we're going to create it. Right, then we're going to say r.push onto it the column. Then we'll do map.set column. No, not the column, the row to the array, and then we're not interested in the non-zeros. We're also going to want to keep track of two more things, right? Smallest row, right? We're going to start at infinity, and we're going to let largest row start at negative infinity. All right, we're going to want to call this the smallest 0 row, and the largest 0 row. And we'll say if this is equal to smallest, since this is equal to 0, we're going to say smallest 0 row is going to be equal to the math.min of smallest 0 row and row. And then we'll duplicate this and say largest 0 row is equal to the math.max of largest 0 row and row. Right? And then I'll just print this all to make it make sense. We'll have our 0 map, our largest 0 row, and our largest 0 row. And our answer just want to make sure that our map looks how we expect it to look. Right, and we're gonna have a lot of things. We don't have zeros anymore. We called it a map. We initially called it the 0 map. We have to change all of these. So we're going to get the wrong answer. That's fine. We just want to check what this map looks like. So we get lucky because the initial one actually requires no changes, but our 0 map, we have a 0 and 0, 1, 2, 0, 1, and 2. In the first row, which is really index 2, we have 0 and 0 and 2. Then we have in the second row, we should have no if mat sub row. Oh, no, yeah, we're looking at the wrong example. This has all zeros. Right, so let's change our example input, just because this one is not really going to be a good determiner of if this algorithm makes sense. So let's just check that this one only gives us 2 keys in our map, right? 0, 1, 2, and 0, 2. Our largest 0 row is 0, and our largest is 1. Our smallest is 1, our largest is 0. Right, so now we want to do our nearest 0 function. So let mat sub x sub y of non-zero is equal to nearest zeros, and we'll pass in our 0 map. Right, and we'll change this to our 0 map. It's going to be a map of number to array of numbers. And like we had earlier, we're going to have our starting row and our starting column. Right, and there's 3 cases that we mentioned earlier. And we want to take the math. Right, there's 3 cases, right? We have to search above, current, and below, right? So implementation-wise, can we reuse anything? Should we do this recursively? We start at 1, 1, right? If we find a 0 in our row, we want to take the min of it. The min of the above row, the current row, and the below row. So our current one that we're finding is going to be greater than our current row is going to be less than or equal to, greater than or equal to our smallest, right? And our max cells, and it's also going to be less than or equal to our max, which is 1, right? Actually, let's check. If current row is equal to our max cell, right, then we just want to, right, so in the case where they're equal, right, we still want to check our current row above and below. It's when we're greater and less than that, it's a little bit simpler. So if we had our current cell, we can just iterate through the last index in the 0 map, and we should be done. Actually, so our 0 map is all zeros. So if we check above us and below us, we should be able to do this in linear time. Now that I'm thinking about it, I keep forgetting we don't have to filter out any ones. So I have 3 cases, right? If, and we're going to need those smallest values again. We'll say smallest row, smallest 0 row, which is going to be a number, largest 0 row, which is also going to be a number. Then we'll pass those in here. Right, and maybe we don't have to do all this passing in. We could have probably wrote this in place, but we'll say if it's the largest, if our current row, right, which is SR, it's less than or equal to our largest 0 row. Then we want to search above, current, and below. So we're going to say above us is going to be SR minus 1, right? So we'd say above is equal to 0 map dot get SR minus 1, right, which would give us an array that we basically want to find. So we'll let min equal infinity, right, and then we'll just return infinity. We'll say 0 map dot get SR minus 1, right, and if it exists, we're going to do for each, right, on the ID X, or the column, right, and then we basically just are going to want to work with min and this is going to be min equals math dot min of min and the distance of S distance of our starting cell, which is SR and SC, right? This is SR minus 1 with a new column here. And then I think we can do this 2 more times. We'll call this current. This is just going to be SR, right, if it exists. And then we're going to have below Now I'm realizing these other cases may not matter, since if we're at the end, right, then we're going to want to check above, current, and below anyway. It's just that these values only mean something, right? When we're not at the top, not at the, well, so for a particular cell, right? We're above it, right? Above us is going to equal something, right? Our current row isn't going to equal anything, and our bottom row isn't going to equal anything. So we can actually delete these extra cases now that I'm realizing it. And then the solution will just be these three values, because we're doing the safe navigation. So if they don't exist, that's okay. Then we actually don't have to worry, don't have to save these since we're not reusing these variables. And then we're going to want to do SR plus 1 here. And then we can remove this and return min. Line 16. Somehow this is a colon. So this works. Let's try it. It should be much faster. End up getting the wrong answer, and my machine is lagging horribly. So we have 10 rows here. Where was our output wrong? It looks like we're matching output, matching output, matching output. Maybe at the end is where we're off. So 1. It's this last row in which we're desperately off. We're off. Right, this last row, we're off by 1. 3 should be, oh no, we're up by 1. So this should be 3. Yeah, we're up by 1, specifically in these cases. So we chose 4, so 1, 2, 3, 4, right? Did we check above us? If we had checked above us, we should get I think I'm seeing we chose this one up here. We had the chance to choose this one here, which would actually give us a distance of 2. 1, 2. But even in theirs chooses 3. Even though the nearest 0 is still here, which is 2. So even that is a little strange. Or maybe I might be seeing this wrong, because this should probably be extended. I wish they made the output bigger. So now I'll be able to see why it's saying, ours is saying 4. Theirs is saying 3. Well, I see, ours is saying 4 because if we go here, we have 4, right? Looks like we might have to propagate all the way up. That would still be n by n time in the worst case. Basically, I think we could fix this if we just kept going upwards. To have the same problem though, if we were in the middle here, there's something that's different though. If we were in the middle here, right, there's still 1 in this row, and all these zeros here. I think there's a distance away that we'd like to stop. We could say while our minimum distance, right, is less than our current row. So our minimum distance, let's just say here is 4, right? We find one over here, right? That's 4, which should be 3, right? Which means the most we want to check is upwards 4 columns because we can't beat that. If that's the case, and we should only check this one, but it should be shorter than that though, because of, I guess that's the biggest one we can do. Be 4 away, 1, 2, right? And this one we'd find one which is 3 away, which means that it can't be more than 3 columns away. Away. So checking the current column, So if here we check the columns, I think when we do upwards and downwards, we could do something like this. We'll say while min, because we know for certain there's always going, I think based on the problem description, there'll always be at least 1. So at least 1 0. So we'll say while min is greater or equal to no. While basically we want to bound our current search going up and down, right? To start, we can always start min, right? We can always check our minimum column first. And then we basically want to check a bounded version of that above us, right? So let's just say we check our individual column, we found 4. We don't want to check more than SR minus 4. We don't want to check anything less than that distance away. So how would we say that? If we find something in this column or any column, right, we basically want to say we don't want to check more, but if we find something in this column, we say we don't want to check more than 1 row or distance one row away. We can definitely find one closer up here. We want to check upwards and downwards. We're having an issue. So we're taking the first one we get based on these two rows, or the smallest one we get based on these two rows. We pretty much have to end up checking upwards anyway. So in the worst case, it would still be n by n time. There's a 0 in every row, basically. Actually, now that I'm thinking about it, we can include the ones as well. Yeah, we can include the ones as well. For example, if we look up our current row, right, and our value is non-zero, right, then we can just say if this one's 3, right, is it smaller than adding 3 plus 1? Or 3 plus the distance between these two nodes? No. Well, we can actually solve our original problem by taking into account the nearby nodes as well. In this case, our zero map just becomes the matrix itself. The zero map becomes the matrix itself. This could still be better. We'll have to come back to this, but this session was actually pretty fun. Yeah, I think it's kind of fun. You know, you stick your mind on something and you hope that it gets to the end, the solution. So I don't even know how much time we went over. It ends up being almost an hour and a half. We only meant to do an hour, but that's actually not bad. This is actually pretty fun. I think we still have to come back to this tomorrow. So I'm gonna say current approach was a scan above and below. Fails on the test below because of bottom 4. Can we reuse zeros? Oh no. Solution, take into account non-zero values. Oh my God, BFS? I think I'm seeing how they're doing this now. But we're gonna revisit this tomorrow. Thank you for, yeah, we'll jump on this tomorrow, day 50.